All right, continuing on with forces. So my learning goal for today, by the end of today, I will be familiar with the term inertia as it applies to objects at rest and in motion, and I will understand Newton's first law of motion. So, in the early 1600s, a guy named Galileo concluded that once an object starts moving, it will continue moving at a constant velocity if there is no friction present. So try to remember they were not able to get to space at that point in time. They couldn't try things without friction, so they had to theorize about a lot of these ideas. So Galileo used this concept of inertia to help explain his conclusion. So inertia is the property of matter that causes it to resist changes in motion. Okay, so the inertia of an object depends on the mass of an object. So the more massive an object, the harder it is to one, get moving, but also the harder it is to stop moving. Okay, so that idea of inertia is worthy of writing down somewhere. Okay, it's the property of matter that causes it to resist changes in motion. Inertia is directly proportional to the mass of the object. Okay, now Newton was born in 1642, and there's maybe some interesting connections here. The year that Galileo died. Okay, so Newton published something called Principia Mathematica. It's a set of 3 books which included much of his own work about physics, as well as a description of Galileo's law of inertia. However, the law of inertia is now called Newton's first law of motion because it was included in his book. His name was on it, so he got the credit. Okay, and here's our first hyperlink. So I'm just going to point out this little green arrow over here. It's a fun little video on the growth of ideas. So here is the formal definition. So the first law of motion. If the net external force, okay, so that's our F net. So that's a really important. That means after all the forces are added together, if the net external force on an object is 0, that means they're all balanced. The object will remain at rest. Okay, and most people are pretty comfortable with that one. That one makes sense. And here's where we start to lose people. Or, even if the F net is 0, all of the forces balance, the object will continue to move at a constant velocity. Okay, and I say that right now and people go, yeah, that makes sense. But you wait. When we start doing some questions, you'll be like, oh no, I totally forgot that. So objects at rest want to stay at rest. Objects in motion want to stay in motion. That's one of the ideas. So here's our huge ideas. Okay, a non-zero net force, that means I have something greater than 0 acting on an object, will change the velocity of an object. The velocity can change in magnitude, direction, or both. That is worthy of a pause and a think, because that's a pretty meaty statement. A net force is not required to maintain the velocity of an object. Another really meaty statement. That's huge. So we don't actually need an external force to keep an object in motion. Once it's moving, it'll stay moving. External forces are required to change the motion of an object. Internal forces have no effect on the motion of an object. So we'll talk about external and internal forces in a moment. I've got a nice little video I'll show you that is kind of fun to watch. If I slide a glass full of water along the counter, normally I would do this on the counter in front of you, and then I stop it really quickly, what happens and why? Well, if you've ever done this, you know that when you slide that glass of water down the table or down the counter and then you stop it quickly, the glass stops, but all of the liquid inside wants to keep moving. Okay, that's the inertia of the water, or whatever the liquid is inside. And normally it goes splashing up the sides and goes out of the cup and all over the counter. So stop and think for a minute. What do inertia and concussions have in common? Okay, well, your brain is basically sitting inside that glass. Your skull is like this hard protective shell around your brain, and your brain floats. Okay, it's not attached to the skull, it floats inside of your skull. And if your head is moving at a certain velocity and then someone stops it really quickly, the inertia of your brain will want it to carry forward. Okay, and when you have a concussion, it's that motion of your brain coming forward and either maybe hitting your skull or impacting that or stopping quickly. That's where you get the serious effects of a concussion. So that's something to really consider moving forward, because your brain is going to be really, really important to you as you move throughout your life. So if I place a stack of coins on top of a piece of paper on the desk, can I remove the paper without upsetting the coins? So if you've got this at home, you can try it. Put a piece of paper on the desk, stack a bunch of coins on it, and then yoink the paper out. If you have some small skill in this, you should be able to pull the paper out without moving the coins at all or even very far. If you're too lazy to try that, then there's two little videos here. There's two little hyperlinks right here and here, and you can get those in the PDF. They're entertaining to watch. Okay, so pause this and think. There's three situations you can have a little think about. So first situation, why is standing up on a moving bus an unsafe and dangerous idea? Well, if the bus stops quickly, it'll be just like that liquid inside the glass, only you'll be the liquid. Okay, so the bus may stop, but you'll have a certain amount of inertia. You'll go flying down the bus, catapulting over the seats or wherever you land. Okay, second question. When your car hits black ice, it's near frictionless. It's that really dangerous ice that's on asphalt. Why is it difficult to stop? Okay, well, it's difficult to stop because there's no friction, so there's no force that's going to oppose your motion. Okay, so you just keep sliding and you have a certain amount of inertia, and without that external force, you're not going to stop. Okay, and lastly, you have snow stuck on your shovel, and you can do this with food on a fork or whatever you like. How could you use Newton's first law to get the snow off the shovel? Well, if you get that shovel moving really quickly and then you stop it, all of the snow that's attached to the shovel is going to have a certain amount of inertia, and it's going to want to keep on moving, and that's why it flies off your shovel. Okay, so here's a quick little link to car safety. Now, as grade 11s, you're starting to get your driver's license, so these types of things become really important. You must, when you're in a car, put the headrest up. It's super important. Okay, so I'll give you a chance. Just read this. This is a really good little problem to read, so pause it. And then down here, okay, go to the PDF on the website and hit the hyperlinks. Okay, there's just a couple of videos about why seat belts and active headrest restraints, headrests, those types of things can save you a great deal of pain and damage if you are in a car accident. Please watch those. It's totally worth your time. Okay, so let's take a quick look at a problem. So determine the missing force. What is the missing force on each FBD? That's free body diagram. So the first question A, we're at rest. So you'll notice we have 12 newtons pointing upward, 8 newtons pointing upward, and we have an FG. So now if this is at rest, that means we need to have some amount here that balances the 20 newtons going upward. So to balance, then this would have to be a force of 20 newtons going downward. Okay, the next one, and this is where people get caught. Okay, this one's moving at constant velocity. Okay, so if you looked here, I have a normal force, that's this one right here. Okay, and a gravitational force or some force acting down, that's 22 newtons. Okay, so now if this thing is at a constant velocity means that the net force equals 0. That is huge. So with that concept in mind, that's where you can say, well, the normal force here must be 22 newtons because it has to balance this force. Okay, I have 28 newtons going to the right, 15 going to the left, and this mysterious F1 going to the left. But if I have an F net of 0, I'm moving at a constant velocity. The only way for this to be balanced or true is if that F1 is 13 newtons. Let's see what we have hidden under here, and there's your answers. Okay, more physics in your car. So you may not know this, but some of your seat belts actually work with the same idea. This is taken right out of your textbook, so if you want to have a read of this, you can. There's a little pendulum inside your seat belt, so when you slam on the brakes, the inertia of that, oops, there we go, moving that around. The inertia of that pendulum right here flies forward, and it's what locks in your seatbelt. So you'll notice if your car stops quickly, sometimes your seatbelt will lock. Okay, but when you're not moving and that pendulum is allowed to move back to its relaxed position, then the seatbelt works. You can move it back and forth and escape the seatbelt pretty easily. Okay, so tried to keep it a little bit short. I know the first one was a little bit longer, so a couple questions to try. Section 3.2 listed on the side. Okay, and thanks for watching.